Do I really need the microphone?
No.
No, right? Yeah. And usually Italian are always loud anyway, so usually we don't need a microphone. Okay, so it's a great pleasure to be here. I actually missed the conference last year in China because of double bookings, and some other colleague of mine presented there in place of me, but in Paris, we are just on the Plateau de Saclay, so it was quite convenient, and it's a great pleasure to be here. So, why mind, body, and Zenoh? Let's start setting the context. Right. Today, there are a couple of topics that are very hot. One, obviously, is robotics. And robotics, if you think about it, it's really about trying to reproduce, whether on humanoid robot or not, but the structural part that make ups, that are useful in the physical world. So if we make this parallel with ourselves, it's really the human body. Okay. And in robotics, obviously, there are lots of mechanical engineers, because that's all the mechanics, then everything else, and computer scientists are like, good spices. They are a little bit everywhere. The second part is mind. Obviously, AI is growing incredibly, and the obvious parallel with AI is our brain. And already there is a confusion, and it's incredible that we still are so confused today, because many people think that the human brain is centralized. Actually, it isn't. And let me clarify this. First of all, your first brain, or the most powerful brain, originally wasn't here. Do you know where it was? It was there, okay? And here we go, for instance, to the Chinese model of body, where they represent the brain here. The original biggest brain was here, because digestion is very complicated. And even today, just for you to know, you have as many neurons as there are in the brain of a dog, just in your intestine. And there is a connection between this brain and that brain, and so be careful, because what you eat, right, influence what you think, in a way, right? But besides that, the other things that is misunderstood is how decisions are taken. I mean, if I catch something, or if I'm an athlete, or if I want to burn myself, many of those decisions and behavior are memorized on the periphery, on our muscle, right? So our intelligence is somewhat distributed, okay? And I think that's an important aspect to recall. But then the question is, okay, we have a mind, we have a body, and I can do things like this, right? But actually, that requires something else, which is the nervous system, which we always forget, right? Because we are fascinated by humanoid robots, we are fascinated by ChatGPT, but then the plumbing sometimes is not so cool. But the nervous system is essential, because unless your nervous system is performant enough to make us do things like this, and let's see if I make it fall, okay, at some time, the body will be clumsy, and the brain, won't be able to do its job either. So nervous system, is the essential things that keeps all those things working together as we do in our body. And thus the question is, where do we stand today? What is the challenge? And the challenge is that the kind of reactivity, the amount of data that we need to deal, and the heterogeneity of the system that we have to deal with. Because again, I don't have any robots, because I came with a motorcycle today, no car, otherwise I would have brought a small robot to give some example. But if you think about the robot today, right, you go from tiny microcontroller, usually up to the data center, and you have to deal with very high volume of data, for instance, dealing with cameras, LiDAR, to very constrained network, perhaps going through serial network to communicate with a microcontroller, or perhaps internet connectivity, or connectivity between radio networks to do swarming. So it's rather complicated, and the news is that this kind of system were not really what we were building 10 or 20 years ago, when most of the protocols that we are using today were invented or introduced. Okay? And so the next slide really kind of try to summarize this. So the building we're trying to build today, the system we're trying to build today, span from the microcontroller up to the data center. Right? That's true for robotics. It's true for automotive. Actually, it's true for medical, and in reality, it's true for most of the systems. And I think the requirements that put us or push us further come from robotics, automotive, and medical, because of the fact that typically we have to interact with the real world. And once you introduce the real world, that means faster reaction times, and usually it means higher volume of data. okay? And then there are some other aspect, which is the ability of operating in spite of reduced connectivity. I give an example. So, suppose that here we had a thermostat controller, okay? Many of those devices that people have at home, you control them with your mobile, but actually the communication with the device is going through the cloud. So you use connectivity to the cloud, you cannot control your home temperature anymore, which isn't very convenient, okay? And so this wouldn't be possible for a robot. And believe it or not, actually, up to maybe 5, 6, maybe even a little bit less, let's say a few years ago, that was a problem. There was a category of robot, I won't show necessarily here the example, but it was one of those companies that make robotic dogs, that they were using MQTT for teleoperating the robot. And then the issue is, well, but if you don't have internet connectivity, how do you teleoperate the robot? Or else, if I'm a firefighter with the robot side by side, why do I need to talk with an Amazon cloud in order to reach my robot? I mean, it's kind of silly, besides creating lots of entropy, okay? Okay, so this is definitely a cross-industry challenge, as I've explained briefly. And, if you try to solve this problem by using technology that have been around in the past a couple of decades, what you end up with is what I call usually a digital Frankenstein. Why? Well, because you have to stitch together different, just to that data flow, different protocols, right? Because there might be a protocol that works on embedded and a constrained network. An example, COPE. But obviously COPE isn't very high performance, so you can't use it if you need, potentially to do any kind of high volume data distribution. And COPE actually doesn't work on the internet either. So you have to bridge it to something else, and usually people bridge it to either MQTT or HTTP. And then perhaps on the cloud you're going to use something else, like perhaps Kafka. So you see, it's stitching together multiple technologies that were invented to solve specific problem when system used to be a little bit more siloed, okay? Systems were living in the embedded, in the edge, and perhaps in the data center with loose connectivity, but those were separate systems, and now we need a single system. So this is true for moving data, but if you try to do data storage, it's even worse, right? Because if you use technology like PubSub, data distribution gives us location transparency, which is a very important property for distributed system. What is data location transparency? It's the fact that in a public subscribe system, I indicate the name or the subject or the name of the topic I'm interested in, then I do not need to know where the data actually is coming from. It just gets to me somehow, right? As soon as I store data in a database, then I lose location transparency, and I need to know where the database is. You think this is obvious, like what the heck are you talking about? Well, this is horrible, because as soon as I try to decentralize the storage, because of scalability, because of co-localization needs, okay, it's a nightmare, because how do I know where I've stored the data? And this is not just fantasy challenges. I mean, we were struggling with this problem. We were doing the smart city in Barcelona, where on one end we wanted to keep data decentralized, but on the other hand is how do you keep track where the data is stored, okay? And so try to solve all these problems with existing technology. It's rather complicated, and you have to add layers on layers on layers to fill this kind of semantic gap, and then integrate to try and hope that everything will work together. So, I mean, it's known that I'm someone that is, an unrested spirit, and lazy also. Okay, because I always say, I mean, it's good to work, not so much. What do I mean with that? I mean, you have to work intelligently. So work once, so that then, anything else you have to do that is routine, it's easy and straightforward. That's the South mentality in a way, right? And as a Southern Italian, we prefer to think very hard and then not to have to work a lot, right? I think that's a good approach. And so, as I was very much bothered by this, around 2015 started to think, how can we address this problem? And then, actually, with Young and some of the other team, many people thought I was just crazy. And actually, big recognition to Young, Sanchi, and so on that some of you might know. He says, oh, actually, this is a real problem. We should really solve it. And eventually, right, we got to Zenoh. So what is Zenoh? The protocol name actually makes a couple of references. One is an acronym, which stands for Zero Network Overhead. And the other one, if you ignore the H or you think that the H can also be read as an N, it's a reference to two philosophers, both called Zenoh. One is a pre-Socratic and the other one is the Stoic. And I think those are both important for me. That's the name of the protocol. If you don't know who are the Stoic, you probably know Mark Aurelius. He was one of the greatest Stoic. Okay. So, what is Zenoh? Zenoh is a pub/sub query protocol. And we are going to try to understand what that means. But in essence, it unified in a single protocol the primitives that you usually find in pub/sub protocol with the primitives that you find in protocol that before Zenoh were not so popular, and they were used for distributed queries. Those protocols were usually named data protocols. Okay. Now, the nice things of Zenoh is that with these simple primitives, we're able to deal with data dissemination, okay, so data in motion, with data address, so data can be stored in no matter what kind of database, because Zenoh deals with the routing of query and then rerouting back of data. But then data can be queried from anywhere on the network if you have the rights. And actually, you can use the same primitive that we use to represent these oracles that are in the network to represent distributed computation. And so all of a sudden, with a very simple protocol that can run, actually I have it. Let me take, usually I demonstrate it, but here we don't have the time, so at least we can take it through here. So actually Zenoh is already here. So you can run it in here, that's an ESP32, and that's already big for Zenoh, okay? And you can run it from here up to the data center, okay? Now, the other things is that obviously we retain location transparency clearly for pub/sub, but also for data at rest. In other terms, you issue a query, you declare the data you're interested in, you do not need to know where the database is. Zenoh will route the request in the most appropriate location depending on where you are on the network at a given point in time. Other important things, we had since the very beginning built-in support for zero copy and shared memory, because that's very important if you want to deal with, again, image processing, LiDARs, and any kind of pipeline that you would find in either AI application, robotics application, automotive, and so on and so forth. The protocol was designed to run everywhere, and as such, we cannot assume IP. Okay, so if you think about MQTT runs on TCP/IP. That's it. Yeah, but maybe here I cannot put an IP stack, or maybe I don't want, or maybe if I'm in a robot, this will communicate through serial with another board. So Zenoh was designed to be able to run as on top of a data link protocol layer. Okay, so data link, just for those of you that are not from networking background, it's Ethernet. Okay, that's a data link layer. So we can run straight on top of Ethernet or anything else. And that also tells you that Zenoh does its own routing. Okay, so we do not need IP to do routing for us. We can run obviously over IP, but we do not need IP. And in general, a Zenoh application can use concurrently links on different networks. Why so? And why is this so important? Because again, I have an application running on my main processor, maybe that needs to communicate through serial with microcontroller, perhaps through, I don't know, maybe Unix sockets, through other applications that are on the same host, and maybe with some other application that is running on a data center. Okay, so Zenoh is capable to do that, and as far as I know, it's the only protocol today that is able to do that. Okay, and adding new links is pretty straightforward. The other important thing is that as we wanted to target a constrained environment, not just constrained in terms of memory or CPU, but in terms of network, we put lots of effort in designing a protocol that was wire efficient. And if you configure it for minimal overhead, you can attain essentially around 5 to 7 bytes wire overhead. That means besides the data that you send on the network, go another handful of bytes. That's nothing, okay? And there are comparisons that we have published, or third party have published with other protocols. Oh, other important things. Actually, as we are in Paris, obviously the first version of Zenoh was written, guess in which language? So who is from France here? Who did the Grande École? Yeah, what did you which programming language did you study in Grande École? OCaml. No? Who did OCaml? Yeah, so the first version of Zenoh was written in OCaml, which is a great programming language. She had, apparently, you had horrors with OCaml. What was your problem with OCaml? You did, OCaml.
Yeah, because it was one of the first languages I learned.
Yeah, but you see, functional programming, it's the first kind of programming that should be taught to students. I think the problem is that if you come to functional programming too late, it will feel strange. I've been teaching functional programming for a few years, and I'm convinced, I've done experiments, that you have to teach functional programming first, and then everything becomes easy, because that's structural thinking. If you go the other way around, it's a nightmare. Because you're used to being pure. And so, anyway, jokes apart. So the first version was written in OCaml. That was great, but it was not practical because not so many people know it. OCaml support for multi-core was still lagging, and so eventually, as Rust matured, we were one of the first companies to adopt Rust in an industrial project, and so we've been using Rust since before the 2018 edition was stabilized, but using 2018 feature, because before that we felt was not mature enough. Why Rust? Well, performance, security, and actually productivity. Because once you become a proficient Rust programmer, that's in our experience 2 times more productive than C++. Okay, so we have 2 implementations of the Zenoh protocol. One called Zenoh, sorry for that. It's like the reference implementation in Rust, for which you have plenty also of API in various programming languages. Pick your own, C# is coming up too. And then we have another implementation of exactly the same protocol, and I put emphasis on that, which is in C for microcontroller. Why not Rust for microcontroller? Well, eventually that's what we would like to have, but the ecosystem for microcontroller is still mostly all about C. Okay, supported OS. Well, obviously, the Rust version runs anywhere where a Rust compiler is available, and the embedded version runs pretty much really on anything. I don't list all the platform because it would take 3/4 of the slides, but it runs even on platform like Flipper. I don't know if any of you knows Flipper. Yeah. So, but anything else spanning from Arduino to FreeRTOS is supported. And we already support also some automotive target. Okay, so let's talk a little bit now about topology. We saw what Zenoh position in terms of a protocol stack. What are the communication topology supported? So with Zenoh you can do peer-to-peer. And you can do peer-to-peer in a click. So a click usually is a graph in which every node has a direct connection with every other node. How do we achieve that? Some protocols do that by assuming that you have multicast. Some other, in fact, require a point-to-point connection between any peer. But Zenoh can also do mesh. Mesh is very important, especially, well, on the internet, obviously, but especially on radio networks. Because when you are on radio networks, connectivity depends on physics and distance and obstacles, okay? So if you have robots platooning, either oceanographic robots or any other kind of robots, usually you need to be able to support mesh. In Zenoh, application can play the role of a peer, and that's a role that you decide at runtime. A peer essentially is willing to route information on behalf of other peers, because if I want to talk between these 2 points, someone will have to route, because either I go this way or I go this way. But in any case, I have to route information on behalf of other peers. But sometimes, I am battery powered, communication takes battery, I'm lazy, I don't want to do this. And so Zenoh supports the concept of a client. A client is not necessarily a parasite, okay, but it's someone that will pair up with the closest infrastructural element or peer on the network and use it to communicate with the rest of the system, okay? And pairing up with a peer is perfectly enough, or it could pair up with a router, because in Zenoh there are software routers. And again, don't think Cisco routers. A router runs on a Raspberry Pi and takes 1% of CPU. Again, it's a Rust application. And then you can obviously deploy a router wherever you want, because you want to scale your system, because obviously you want to add hierarchy, because for instance, we have hierarchical routing, so routing at the peer level or routing between routers, those are two different domains of routing, which is good for scalability. And by default, we use slightly different routing algorithm between peers and routers. And as of today, actually, the routing algorithm is not something that you, as an end user, can plug, but probably, maybe by the end of this year, we'll make it pluggable. Because depending on the application, we want to be able to use perhaps the routing algorithm that really fits the kind of additional constraint that they might have on their topology. So if we put all of this together, this means you can build a system in which, again, I can have one application here working as a peer, communicating through serial with this client, TCP/IP with this peer, Unix PI peer, and so on and so forth. And notice that data from here could flow, just about anywhere, and the application are completely shielded. They just use the Zenoh API, which is very simple, very high level. You don't need to know about topology, you don't need to know what transport I'm using, you don't need to know where the data is stored. Everything is completely location transparent, and as we will see, quite performant. So if we put this into perspective, these are the kind of topology you can build with Zenoh. So essentially, Zenoh doesn't give you a constraint. You build a topology that makes sense for your system. This is the topology that MQTT enforces over you. And this is the topology that DDS, that is a very famous standard for PubSub, enforces over you. And again, the reason, I think it's interesting to make a reflection. So MQTT provides you with PubSub, DDS provides you with PubSub, Zenoh provides you with PubSub plus distributed queries. But you see that although, the API might be different, the abstraction are the same. But MQTT and DDS impose on you topological restriction on the topology that your application has to comply with in order to leverage the PubSub abstraction. Zenoh doesn't impose that constraint on you, which I think is very important if you try to build the system that we just discussed. Okay, now you have to understand that Zenoh, a few years ago, now it's a very popular protocol, but a couple of years ago was a newcomer. And when you are a newcomer, it's for you to adapt, okay? So when we designed Zenoh, we decided since the very beginning that we wanted it to be easy to integrate with existing protocols. Why? Well, because existing protocols were already deployed, we knew people struggling with certain problems, and I'll discuss a few. And if we would allow those people to use Zenoh without changing a single line of code in their system, would be bingo. And this is actually how Zenoh became very popular, and I'll give you some examples in robotics. So Zenoh has two kinds of plugins. You can plug in protocols, so we have plugin for DDS, for MQTT, and by the way, if you just realize for a moment, you could actually create a decentralized MQTT network just by activating MQTT plugin on Zenoh routers. And that's what some of our customers do today to scale their MQTT application without changing a single line of code. Okay? And we have plugin for databases because we deal with data at rest, but obviously we don't want to write databases. Right? There are lots of great databases. And the nice thing of Zenoh is that as far as we have a plugin for a database, they can become storage somewhere on the network that can store data, and you can query them without knowing actually what kind of database you're dealing with. Okay, so that's another level of transparency we introduce. Okay, how about performance? These performance are coming from a paper that was published from NTU, National Taiwan University. There is a group, there is a very active user of Zenoh over there that contributes also to AutoWare. And what they were comparing here were MQTT in green, Kafka here in red, DDS, this was Cyclone DDS implementation in blue, Zenoh with routed communication and Zenoh peer-to-peer. So
it's
what they were
Kafka
measuring,
Streams or Kafka? Kafka Streams or Kafka?
Kafka. Okay. So let me explain the topology. So first of all, this was tested on a 100 gigabit network. Okay, the configuration was throughput and latency between a producer and a consumer for technology that support peer-to-peer, or else between a producer, the mediating node, so a broker in the case of MQTT, a router in the case of Zenoh, and Kafka servers in the case of Kafka, and then a consumer. And in this case, every element was running on a different machine connected by 100 gigabit network. In this machine, iPerf was saturating at 70 gigabit per second, and here you have millions of messages per second. Here is the same graph, but in gigabit per second. So this is the throughput from megabyte to 200 gigabit per second, logarithmic scale, and this is the payload from 8 bytes to 512 megabytes. Zenoh has no limit. In Kafka, there are some limits that you have to change by configuration. That's why the graph stops here. So what you see here, and again it's logarithmic scale, that for instance, at 8 kilobyte payload, Zenoh reaches a peak performance of 69 gigabit per second. That's Zenoh peer-to-peer. Zenoh routed, it's 46, and DDS, which is pretty high performance, before Zenoh was considered as the most high performance communication protocol in the market, is around, well, a little bit lower than 20 gigabit per second. MQTT at 6 and Kafka at 4. So how do we do that? Well, it's protocol engineering, it's implementation, obviously. Okay? And if you look at latency, because as you know, there is a trade-off between throughput and latency, Zenoh latency is actually pretty good, okay? Because it can go off the shelf 10 microseconds in that scenario, but then if you use expedite data, which essentially disables the automatic batching, okay, and the network scheduling, you get down to 6 microseconds, okay? Just to give you some context, in Zenoh, we have, whenever you produce data, we do some scheduling, okay, to try to optimize the resource usage, reduce CPU utilization, reduce the number of system calls, maximize network utilization, and maximize throughput. That has an impact on latency, which you see here. This is why it's 10 microseconds, which is still very, very slow, okay? But then if you have absolutely latency critical application, there is this concept in Zenoh of expedite data, where in that case, you are not traffic scheduled. You go straight on the network. Okay, in that case, the latency is 6 microseconds. Okay, so by the way, as we started later, when am I supposed to finish? Because
You haven't started.
it's not 10, no, because we started later.
Late, 15 minutes.
15 minutes late, so I have still, okay, up to 25, is that right? Okay, so we're still lots of, great. No, because I didn't want to rush, and so we're perfectly good on time. Okay, so let's look at the programming abstraction. So Zenoh provides, as a programming abstraction, primitives that operates on named data. Okay, named data is something like this, right? It looks like a path or a URI. So both one sense or speed 25 would be a Zenoh resource, which is composed by key and value. Now, Zenoh has just 2 primitives, okay? One is pubsub, and again, this is logically pubsub, right? We already saw that there are multiple topology over which this abstraction can be implemented. So there is a publisher and some interested subscriber receive data, obviously. And the other one is query and queryable. So a queryable is an oracle on the network that tells, look, for this key expression, or this set of data, you come to me, I have answers, okay? And so whenever an application issues a query, literally what happens is that Zenoh knows the queryable that are on the network, looks at your query, and does a simple between quotes, a set cover operation, okay? So follow me. A query describes or defines a set, okay? Now, if I want to solve this query, I need to understand what are the set of set, okay, that covers the set for which I'm looking data. And as I'm in a distributed network, there might be multiple set of set that cover this query. And depending on where I am on the network, right, I need to understand what is the closest set of queryable that can answer my query. Because if I'm here, maybe the three of those will be the perfect place to go and fetch the data I'm looking for. But if I'm on this side of the network, maybe it's the three of you. Okay, that's what Zenoh does. And that's great because all of a sudden, right, you can easily scale out. You have fault tolerance, you have location efficiency, because depending on where I'm on the network, so if I'm at home or if I'm in New York, perhaps the same data will be fetched in different places depending on where it is available on the network. I know this sounds abstract, but this is really how it works.
But
And
how
if
you
you're
know?
familiar-
How you know about?
Sorry?
How you know where you are on the network?
How do I know?
Yes.
Well, because let me go back real quickly here. Because you have a session with somebody,
Okay.
right? And I tell you something else. There are some projects we are working on in Japan on road mobility, in which actually they don't trust your GPS. Because you can fake your GPS.
Right.
You can't fake your 4G or 5G session with the antenna because of physical reasons. Okay? And so the location is always inferred. So the actual GPS location wouldn't be where you are exactly, but would be the location of the cell where you are. Okay? But again, now I hope you have the answer to your question. Okay, so these are queryable, and then, right, once Zenoh figures out to who to route the query, he will route the query, the queryable will be triggered, and will answer with a finite stream of answers, okay? And Zenoh has a protocol to let you know, when the answer from a given queryable are over, and the answer from the entire query is over, okay? Okay, so in terms of programming API, how do you publish data? Because it's good to show code. We are engineers, right? So you can use asynchronous or synchronous programming, but if you use Rust, I think it's much more handy to use asynchronous because all of a sudden you don't have inversion of control, okay? So you, in this case, I'm using the default configuration, I'm opening a Zenoh session, and then I'm writing, we are in France, so I'm writing a daily quote in French, je pense donc je suis. Cogito ergo sum, right? So that's it. You don't even need to create a publisher. A publisher in Zenoh is just a bunch of optimization that we might do, but in terms of protocol concept, a publisher doesn't exist, okay? How do I subscribe? Well, suppose that I wanted to receive quotes for every language. Then if I have a session, Z declare subscriber, daily quote, and that's it. And what I get here is a stream. So what do you do with a stream? You just iterate through it, right? So it's pretty straightforward. Whoops, I never use this stuff because I keep pushing, okay? So in here you could do a while let, you could do, however you would use a stream in Rust, okay? This is why there is no callback. Everyone knows what is a stream? Some do, okay. Think of it as a container. When you have a vector, but the vector, it's already filled. The difference in here is that this is being filled as data comes. And that's one of the nice things of asynchronous programming, okay? It looks like sequential computing, but it isn't, okay? That's why you have the lack of inversion of control, and that's good for code clarity, it's good for reasoning, and so on and so forth. How do you declare a queryable? So in this case, I'm declaring a queryable. Suppose that I wanted to have in the network, this agent, that when you ask for a quote in a given language, we provide the quote. I could do that with a queryable, okay? So that's how I declare a queryable. Complete, I don't have time to explain what it is. For those of you that know what are quorums, it has to do with quorums and implementing quorums. If you do not know, never mind. And if you're curious, we can discuss after the talk. And then how do you issue a query? Well, you just do a get with a key expression, and then there are some other things that you can use to decide or control better actually who gets the query and whether the data is consolidated on the way back or not. So let's take an example. Let's assume that I had a bunch of robots and I have queryables that allow me to query the status for the robot. Okay? So if I want to get the battery status for bot 1, I could say get bot 1 status battery. Zenoh will figure out that that's the only queryable that it can answer, and you will get 80% back. Then I could say, well, actually, I want to get the battery status for all the bots, and this is the key expression that you would use. In this case, Zenoh will do the set cover, see that has to reach all of them, and you will get answer from all of them back to you. Then I could say, well, you know what, I want to get the battery status from all robots, but only if the level is inferior to 50%. So they will all get the query, okay? This will say, okay, nothing to give, and the other one would provide back the value, okay? So that's just to give you an idea of how the basic queryable works. Okay, so you can compose an abstraction, obviously to support PubSub, remote computation, and storage. And storage are just a combination of a subscriber and a queryable, nothing else. Okay, let's look at who is using Zenoh today. The first user of Zenoh actually were telecom and industrial, but the biggest user of Zenoh today are robotics application. And there was a very interesting study that if you have not seen it on the internet, I suggest you look at it. This study was produced by Alphabet Intrinsic, which is Google robotics arm, and the Open Robotics Foundation. It's sufficient to search for R&W alternate on Google, you'll find it immediately. And this report was looking at the challenges they were having while using DDS, especially on wireless network, and then did two things. Asked the community, what do you want to see in ROS, which is the most popular robotic platform on the market today, as an alternative, and also did an analysis of virtually all the protocols that are applicable to robotics and tried to see how they rank with respect to the requirement. And the result there was that Zenoh ranked first. Okay, so this is the Excel that maps the requirement, and actually this is what the user were asking for. So Zenoh was number one. As a consequence of this, Zenoh is the first non-DDS protocol to become now tier 1 within ROS 2 with the Kilted Kagyu releases. And I mean, even before this, we have plenty of users that are using Zenoh deployed on the robot already. Why? Because they were having massive problem sometimes to communicate over a wireless network or across the internet. And thanks to our protocol plugin, they would just deploy a router with a DDS plugin inside the robot and talk Zenoh with the rest of the system. And I'll show you an example of a car actually that was doing that for the India Autonomous Challenge. Now the community, it's quite let's say, excited about this, and it has becoming borderline embarrassing because these are the kind of memes that you see circulating also on you saw this on LinkedIn. I mean, we have lots of pressure, but I think it's good when you start seeing this stuff, and there are worse memes than this, but this was cute. Okay, automotive. So this is a Dallara, beautiful Dallara, an Indy format car. No, that's not Formula One, and it's an autonomous car. This is the Indianapolis circuit. And actually, this is a nice story because the car is running ROS. Okay, this was full COVID. It was 2020 or 2021. Can't even recall the exact date. So the car is running ROS, and they are supposed to communicate with the box through a 1 megabit, let's say, real-time wireless network called CARB. It's a Cisco technology. And there are lots of constraints. You have the constraint of the number of packets you can send, the maximum size. So they assemble the car, they put ROS, they try to operate it. They literally kill the Wi-Fi routers. Literally, they make it crash. And so they didn't know what to do. And so as we were involved in this, we said, well, I mean, just drop a Zenoh router on the car and make sure that they talk Zenoh across the Wi-Fi. You don't have to change anything. And so they had two routers, one router in the car, another router on the application side that they were using to teleoperating or receiving the telemetry, and this is how they managed to make it work.
So you are saying that V2X is not 802.11p or V2X?
No, it's CARB. It's a commercial
okay.
product, yeah. And again, the reason is that with CARB you can have multiple channels. Every channel is fixed bandwidth because you have multiple teams, and so they didn't want one team to use more bandwidth than other because it would be unfair on a competition scenario. The network, you can check it out, CURB.
Okay.
Okay, other deployments of Zenoh are in autonomous train. So here you have Zenoh Pico on the controller portion of the train and Zenoh for, let's say, V2X. There is a recommendation from ITU toward standardizing Zenoh for use in intelligent transport system communication. Eclipse SDV, which is the software-defined vehicle initiative in Eclipse, growing very quickly, has embraced heavily Zenoh. And there are projects like uProtocol from General Motors that are entirely based on Zenoh. uProtocol is General Motors stack for EV, electric vehicles, and autonomous vehicles. In other verticals, there was this interesting article written by Richard from AWS in which he was analyzing the protocols that were available. This is from 2017, 2023, the 17th of January 2023. He was looking at MQTT, he was looking at DDS, COPE, and so on and so forth. He said all these protocols have limitation, the kind of limitation I've described, and actually looks like Zenoh is the way to go and the viable technology for building the IoT system that we should be building. We have lots of application, an increasing number of application in medical, and that's one of my favorite domain because that's where we can help usually most people that need help. And some interesting application in aerospace and defense. My favorite is air traffic control management. In fact, the biggest air traffic control management system in the world that is being built now, it's called Blue Amazon in Brazil. Brazil is a huge country. That's entirely based on Zenoh 2, which is quite cool. Okay, and it's an horizontal technology, so it's normal that we have more and more application using it. But the bulk of it today is robotics. We have application on distributed analytics, which is quite interesting because there is a combination of a cryptocurrency called CryptoRat and a distributed analytics platform that works a little bit like Sekietom that allows you to give computational resources. Data scientists that need to crunch numbers would use these distributed resources, and then you get paid by crypto. All that infrastructure is also running on Zenoh. Okay, summarizing. Okay, Zenoh is one of a kind of a protocol because it's the only protocol still today that unifies that in motion, that in computation, and remains very, very simple to use. It has no topological constraint. And actually, it's very, very easy to use. I mean, I gave you some code snippet in Rust, and we didn't go beyond 3 lines of code. Try to do the same with DDS or MQTT. Okay, good luck. Performance are great, and we are unrestful, so we continue to innovate because you are never. My principle is that you are never done, and that's what I always tell to the team: you are never done. Because once you are done, you consider you are done, it's like you are dead, right? There are always things we can improve. And we have done, when we think we are done improving, we start from scratch again. That's my philosophy. That's it. Thank you very much.